Safina, am I audible to you?
Yes, ma'am.
Okay, so last class, I think you weren't there. We have completed till this resistance part. So let's move forward. This question was done, and I think students could write also this question. This was left. So coming to the other portions that are there in this chapter, you have to calculate the resistance. So basically, the formula of resistance that I discussed was rho L by A. Now here the area is pi r square because you'll always have to consider the cross-sectional area. This is the area. So resistance will be rho L by pi r square. This is how you have to check the resistance. Now when we calculate the resistivity of the material, if you have any figure where two faces are given, like a cuboid, and between the two faces you'll have to calculate the resistivity, a resistance or resistivity, anything. So what you do, actual formula of resistance is rho L by A. So here area will be the dimensions, means A into B for a square, not a square, sorry, for a rectangle, because all individual pieces are actually rectangles. Now this 1 is this figure. This is 1 and this is 2. Means when you have a cuboid, basically you can say the right and the left, the extreme right and the extreme left faces. So how to solve it is r is equal to rho. Now for the length you take the separation between 1 and 2. Separation between 1 and 2 is given as L by area. Now area of one side. This is breadth. This is the height. So that is B into H. Rho L by BH. This is how we'll have to write for the first part. Let's say the second part. See, 3 and 4. 3 and 4 means the front one and the back one. The front face and the back face. These are your 3 and 4. So what you do, resistivity will be the same. R is equal to rho. But for the length, you're going to take the separation between the front face and the back face. See, from the figure, it's clear. This face, this side, and you can see this, they are separated by the breadth. B is separating them. So this will be rho B by this. The face is what's the length of each face? Height multiplied by length. That is L into H. Teesra, resistance is equal to rho. Now, the length, fifth and sixth. See, fifth is the topmost one, sixth is the bottommost one, like this. They are separated by a distance of h, which is the height, divided by length. The area of each face is breadth into length. That is L into. This is how we have to calculate. Okay. So write down these two portions. Then we'll discuss conductivity and conductance.
Ma'am, how is it L into B? Ma'am, how is it L into B?
Where?
Ma'am, in the second question, third question.
Third question, L into B.
The third part.
This third one.
Yeah.
See, this is each face is like this, the top one. See, the length is L. This is the breadth B. So area will be length into breadth. Now clear?
Yes. Done.
Okay. So, coming to the four small topics that you should know: conductance, conductivity, the current density, and the mobility. These are four small topics that play a very important role. Out of these, conductance and conductivity do not come directly in the exam as it is, but they are used in the numericals. Like instead of the resistivity, conductivity will be mentioned. Now solve the question, and what you will want will be the resistivity. So you can just solve it. It's very easy. I'll tell you. The conductance is basically the inverse of resistance. This is represented by the symbol G. This is just inverse of resistance, that is 1 by R. So suppose in a question you don't have the resistance and you have the conductance. Just take the reciprocal of it and the conductance will be used. So this is the first term, conductance, inverse of resistance. Resistance is SI unit is ohm. SI unit of conductance will be ohm inverse. Then conductivity. Conductivity is inverse of resistivity. The symbol of conductivity is sigma. Inverse of resistivity means 1 by rho, where your rho is resistivity. And conductivity is actually even more important than your conductance. Conductivity is more important. Now, this is ohm meter. Usually, the unit of it is, so that will be inverse. Ohm inverse, meter inverse for it. So these are two basic terms. Individually, these aren't asked. Numerically, they are used, and that too, conductivity is more used. And it is a common term that we study because it has a lot of applications. Then current density. Current density is very important. Current density is basically current per unit area. That is, if let's say I have a wire segment. Okay, this is the wire segment that is present. Here, some amount of current is flowing and the cross-sectional area is A. So current density is represented by the symbol J. It is current per unit area. Means in 1 meter square, how much of amperes of current is flowing. Ampere per meter square is its SI unit. It's a vector, means direction is same as that of the current. Now, this is very important. What's the microscopic form of Ohm's law? This is actually important, and this has been asked a lot in the exam. So, the any earlier, I think before last to last year, I wasn't even discussing this question, but I have seen last 2 years this question has come a lot. So you pay attention to it. What is the microscopic form of Ohm's law? See, I is equal to NEAVD. This is the current's value, NEAVD, and drift velocity is E tau by M. Now, when you put this drift velocity's value in current, you get NEA, and instead of VD, we can write E tau by M. Now, see from here, one where this electronic charge will be multiplied. So it is NE square A tau E by M. If I bring this A down, I'll be left with I by A, NE square tau by M into E. Now, current density is what? The current per unit area is actually current density, that is J. J is equal to NE square tau E by M. Now, resistivity, we discussed it in the last class. Resistivity is actually M by NE square tau. So, NE square tau by M will be 1 by resistivity. So, basically, when we put the values, we get the current density as 1 by resistivity into the electric field. Fine. So, 1 by resistivity is sigma. So, basically, microscopic form of Ohm's law is the conductivity multiplied to the electric field. E is your electric field. J is the current density. Sigma is the conductivity. Conductivity. This derivation comes a lot in the exam to write. Last is mobility. It's the drift velocity per unit electric field. That is take drift velocity divided by electric field. It's just a ratio. Physically doesn't have any meaning. So these are four terms which you should know. Now do one thing. For this part, just take the screenshot. For the derivation, you write it by yourself because that is very important. Okay, just take the screenshot.
Ma'am, J is equal to 1 by rho, right?
J is equal to
1 by rho. So,
1 by rho. Yes. So 1 by rho is sigma. So sigma into E. Rho is resistivity. Resistivity and conductivity are inversely proportional. The formula which you have written. So in short, the microscopic formula is J is equal to sigma E. What's the confusion, Safrina?
no, ma'am. Over here, rho is equal to m by n e square by tau.
Yeah. Yeah.
The E, where did it go?
E was already there, no? See here. This electric field came because of the drift velocity from here. This electric field stayed here. Now see, we just identified, we first shifted A in the denominator, so we were left with E till here. I by A was J, still E is coming. I just told that this whole part is 1 by rho. So we have replaced this with 1 by rho. Electric field was still there. In this formula, we have
Oh,
just put the value.
oh, okay.
Okay?
Okay. Ma'am.
Just take the screen shot of this page. Done? Now, this is also very important. This part repeats itself in semiconductors chapter as well. Temperature dependence. All these initial topics are very important of this chapter. This chapter is not so lengthy like your first chapter and the second chapter. Those chapters were very lengthy, especially the first one. First chapter and fourth chapter. These two chapters are very lengthy. We'll have to, we had to give a lot of time in the fourth also in the class. So, anyways, temperature dependence of resistance mean that if the temperature is changing, so will there be any change in the resistance or resistivity or not? Now, reason is that length and area are the two factors which differ resistance and resistivity. The resistance and resistivity, they just differ by ln A. See, R is equal to rho L by A in the densities formula. When you put everything, the area and length get cancelled off. That's why here you don't have area and length, while here you have this area and you have the length. It's a major difference, which is differentiating them also. But when you have a temperature range, when the temperature changes, the change in the area and the change in the length is very small. So there is no significant change in resistance or resistivity. Resistance will also change with the same amount, resistivity will also change in the same amount. Now, few graphs are there. You'll draw them properly, write the theory part also well for them, and these are very important. Because see, the current electricity chapter gets related to your semiconductors. You study here everything about conductors. There, everything will come similar, but with the term conductors. Now, conductors mostly mean your metals. What happened here is that initially till 0 degrees Celsius or 273 Kelvin, the graph is non-linear. The density and the resistance, they increase non-linearly with the temperature. But at a temperature which is 0 degrees is crossed, the graph becomes linear, means the resistance or resistivity directly increased with temperature. So this is what is written over here, that see, When temperature increases, relaxation time decreases. Relaxation time means when two electrons are colliding. Then they take a momentary rest before they begin their next collision. So it says tau is decreasing. Tau decreasing means this average relaxation time decreases. Because see, average relaxation time means body is taking a lot of time to prepare itself for the next collision. Now, temperature increases, body's randomness will be more, so the tau will be less. Means there won't be much time for the electron to actually rest. It's something like this. Then resistance and resistivity will increase. Why? Because of the formula. Where was the torque line? Torque, I'm saying. Where was this relaxation timeline? So T increases, but N remains constant. So this is how we get the graph. Non-linear, but a straight line after 0 degrees Celsius. For alloys, it's the same story. It's just that the variation is very small. Here, there we have the small variation, not a variable variation. Variation. This small gap gives a small variation. Okay. Resistance and resistivity, they increase. They still increase directly, but with the variation is very small. Then come your semiconductors and insulators. Now see, the graph will be exactly opposite because temperature and resistance are completely opposite. So the graph here is a hyperbolic graph. Yeah? Conductors, alloys, and semiconductors have this story. There's a material superconductor. Superconductors basically see, these are those materials that are actually not conductors, but once a temperature is reached, they behave like conductors. Those are known as superconductors. Okay, uh, means initially they are behaving like non-conductors, and as soon as a temperature is crossed or that temperature is received, they'll behave as if they were semiconductors or insulators. That's why they are called superconductors, and this is what we get. Okay, critical temperature, once it is crossed, critical temperature has to be crossed. If the critical temperature is crossed, then the body will have the variation like the conductor. That's why they are superconductors, means not conductors usually, but once the temperature is crossed, then they behave like superconductors. They behave like conductors, but this is not very important, this one. So this, you can just take the screenshot at the end, but the rest of it you draw, then we'll discuss the formula for resistance. And directly we move on to the internal resistance part then. Few portions are left, let's complete it.
Done. Done. Done.
Okay, let's see the formula of variation of resistance with temperature. You don't have any derivation here. You just need to remember one single formula. See, variation of resistance with temperature basically is that resistance, let's say we have some resistance at the room temperature. Okay, this is the resistance at the room temperature. Now, resistance at this room temperature is equal to the resistance. This T temperature is, it could be known to us or unknown also. Okay, this is not the room temperature. Room temperature, I'll be representing it through a naught. RT is equal to R naught. Fine. RT is equal to R naught. Now, here 1 plus alpha T minus T naught. See, let me just tell you what are the symbols in this formula. Look, RT is the resistance at any temperature. If I talk about this RT, this temperature could be given to us. Sometimes the task could be to find out this temperature. So this is the temperature, any temperature. Temperature. R naught is the temperature, the resistance at the room temperature. Means here the room temperature will be used. Now see this T that you see, this is that temperature, that any temperature that I have taken, this is that. So at this temperature, you will be getting this resistance. Okay, and T naught is what? T naught is again this room temperature. So at this temperature, you will be getting the other resistance. Alpha is just the coefficient. Everything has been written below. Okay, look at this theory part. T is a certain room temperature. T naught is the room temperature. Room temperature will be provided to you. If not, you can take 37 degrees Celsius, 25 degrees, 25, so not 37, 27, 25 to 27 degrees Celsius, but that will be given to you. You don't have to remember it. Resistance at any temperature T, resistance at the room temperature, temperature coefficient of resistance. Now, this alpha, few things on this alpha depends on the material, means different materials will have different values of this alpha. SI unit is Kelvin inverse because resistance part will cancel it. Now, depending on alpha, you can understand what kind of material it is. For conductors, the alpha is positive. Alloys is also positive, but it is small. Since remember, the variation was also very small. And semiconductors, it's directly negative. Okay. Now let us discuss one numerical based on this. This question is from your NCRT and has come in the board exam as it is without single change. This is an electric toaster uses nichrome for its heating element. When a negligibly small current passes through it, its resistance at the room temperature. So see room temperature is specified to you. So which variable is this? T naught. Yeah, T naught. Correct. This is the room temperature. So at this room temperature, which is 27 degrees Celsius, you can convert later if needed. Is 75.3. So what is 75.3, Safrina?
R
R or R naught?
R
R
okay.
naught.
R not okay.
Because at room temperature it is this. 75.3 ohm. When the toaster is connected to a 230 volt supply, so voltage is 230 volt, the current settles to 2.68 ampere. Okay. What is the steady value of temperature of the nichrome element? Steady value of temperature of the nichrome element, and it has given us alpha is also 1.7 into 10 to the power minus. So basically, temperature we have to find out. That T we have to calculate, which is missing in this question. Now, in the formula, we saw that for T naught, you will have R naught, and for T, you will have R. That's what we studied. Now, see, here the resistance is directly not given. You will have to apply the Ohm's law first. Okay. Ohm's law is V is equal to IR. So using that, I will be R, not I is already there. This resistance is equal to V by I. Resistance is equal to 230 divided by 2.68. This is the resistance. Now this is the resistance, this much of ohm at the temperature. Only one is missing. See, this resistance at this temperature RT is equal to R naught 1 plus alpha delta T. You can use delta T also simply instead of writing T minus T naught at all. But here in this question you will have to write because this is missing. Your delta T will be equal to T minus T naught. Now you put all the values. RT will be 230 by 2.68. R naught is 75.3. 1 plus alpha is 1.7 into 10 to the power minus 4 into delta T is 27, T minus 27. So see, one variable, one equation. You just have to find out this. Got it?
Yes.
Okay, I'll start with internal energy in the next topic. For this, just copy down this part, this formula and the solution, the question.
Um, um, Ma'am, for the alpha, will it be degree Celsius or Kelvin?
This, see, for here in this one, how to put it? You can take it in inverse degree Celsius also. Okay, no need to convert it into Kelvin because this is getting multiplied to the temperature, which is already a change. Okay, that's why you don't need to convert. But resistance, you'll have to ensure that this is in ohms. And temperature also, you don't need to convert here because there's a changeover.
Okay.
Okay.
Done. Done.
Just a minute, Sabrina. Okay, see, Sabrina, now coming to the concept of internal resistance. Internal resistance, if we elaborate a battery, so let's say this is the internal battery, okay, the battery of the cell, basically, the cell is there. So in a cell, what all things are present? There is one electrode, okay, here, two electrodes are actually there. Two electrodes are present and they are dipped in the electrolytic solution. What all things are there? These are the two electrodes present, cathodes, anodes, those things which you study in chemistry. And this is the electrolytic. But I think you have a chapter. Electrochemistry is there in chemistry. So
Yeah.
there have you done those ions that come off in the electrolytic solution and all the reactions must be there, something like this. Yeah. So that part is the same. It actually occurs, the same thing is there. But right now, what we are concerned with, see, whatever will be the resistance provided by these ions that will be coming off and going to from anode to cathode to anode, whatever it is. So they will be providing resistance. And the resistance provided to this battery, to the cell, that is known as the internal resistance. It is always marked beside the battery like this. This is the EMF of the cell. This is the resistance. There is the internal resistance represented by a symbol R. SI unit is ohm. And see, total resistance here will be the external resistor also plus the internal resistance. You will not neglect the external resistor, right? Now, second topic is EMF. What is EMF of the cell? See, EMF, or you can say electromotive force, it's basically the maximum potential difference across the terminals of a cell in an open circuit. Open circuit means when the circuit is off, switch is open. Now, E is for EMF, but it's voltage only. The term is electromotive force, but it's not a force which is present. Okay, difference is that whatever is the voltage for this, whatever is the voltage across the internal resistor, that is your EMF. And whatever is the voltage across the external resistor, that is the terminal potential difference. So current will still be voltage by resistance. Now resistance is total. This is the internal resistance and this is the external resistance. And this is the EMF. Okay. So this is the EMF. Then talking about the terminal potential difference, it's the potential difference across the terminal in a closed circuit. Means across the external resistor, whatever will be the potential difference, that will be the terminal potential difference. See, let's say there are many external resistors connected. Now we are not concerned with any of the external resistors. Okay, we are not concerned with any of the external resistors. If many external resistors are present, how will we use it? How will we solve it? That we'll see in series and parallel connection in the circuits. Right now, you just have to see all of these are finally connected. Even if a single resistor is there, all of these are present, and this is our R equivalent. Here is a cell battery, you can say. Battery means a group of cells. So usually we take a cell also. So this is present like this. Now see, this is the internal resistance. This is the EMF of the cell. So here for this part will give you the EMF. That is the potential difference for this internal resistor. While you will have this point here, whatever will be the potential difference, that will be the terminal potential difference. Terminal potential difference across external resistor. Now the formula that you have to remember is V is equal to E minus IR. So potential difference here is divided into two parts. Potential difference across external resistor and across internal resistor. We are going to use Ohm's law. So potential difference across external resistor will be I into R, and across the internal resistor it will be I into small r. Okay. So potential difference is equal to potential difference across the external resistor. That is the terminal potential difference. Okay. So we will take we'll take this as V is equal to E minus I into small r. But depending upon the questions, you can use any of the formula. Like this is one question, let's see. This says, this is the external resistor connected. Capital R is 10 ohm. Now it could be there that instead of giving one just single 10 ohm, it can give you a circuit like this. One connected like this, one more connected, and finally you will have to reduce and make your R equivalent. To make the question a little tough and to see whether you actually know the series and parallel combinations or not, it can combine it here also. That can also be done. But anyways, let's see. Right now, let's say final external resistance is 10 ohm. Internal resistance is 1 ohm. Voltage is 22 volt. First part is current. Current is equal to EMF divided by small r plus capital R. The formula of it. 22 by 1 plus 10, that is 22 by 11, which is 2 ampere. Clear? Then it says potential difference across the external resistor. E. When we talk about the potential difference across the external resistor. Potential difference across the external resistor. This is equal to I into capital R. Current is 2. Now external resistance will be put, that is 10, which is equal to 20 volt. Third part. Potential difference across the internal resistance. So I into small r, that is 2 into 1, which is equal to 2 volts. Look, are you getting the voltage back or not? Across external internal, 20 plus 2, 22. 22 was the actual supplying voltage. So you can see how it is distributed. 2 volt is coming to the internal resistor while 20 voltage is coming to the external resistor like this. Finally, it says terminal potential difference. Terminal potential difference, by looking at the second part, you should know your answer should come 20 volt because it's the same thing across the external resistor. But let us go through the formula and see are we correct or incorrect. EMF of the cell is 22 minus current is 2. This is 1. So 22 minus 2, that is coming 20 volt. And as per this part also, it should have been 20. Okay, clear?
Yes.
Okay, one or two things I'll tell you. See, um, just this, or I'll tell it later. Just do one thing. Till here, till this part, take the screenshot. Okay. And from here, just write down the formula part. Otherwise, you'll be very confused and just copy till here. But starting part, just take the screenshot. No need to write it.
Done, ma'am. Done. 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 Completed.
See here, there are two equations. Usually, the equation that we use is discharging of a cell, where current comes out of the positive terminal of the battery and this is entered through the negative. That is usual case. What happens from the positive terminal, the charges are discharged, means the current comes out. This is known as discharging. Okay, and if the current comes out from the negative terminal of the cell and enters the positive one, that is known as charging of the cell. So in that case, just in case if you see any equation where you see the current is moving in the opposite direction, or it has clearly mentioned that charging word is used, then directly use the equation V is equal to E plus IR. Don't use E minus IR in that case. This is for discharging and plus one is for the charging. Okay, now if key is open, I is equal to 0, V is equal to 0. Now this part I'll tell you means if I give you this graph, in this graph, at this point, current is 1 ampere, but voltage is 0 volt according to the axis. Similarly, at this point, this is 6 volt, but current is 0 ampere because x-axis coordinates are not there. This says that plot of variation of potential difference across a combination of three identical cells in series versus current is given. Okay, what is the EMF and internal resistance of the cell? See, what do we have from here? What do we have from here? If I look at this here, the current given is 1 ampere, while the voltage given is 0 volt. Okay, if I use V is equal to E minus IR as one of my equations, okay, V is equal to E minus IR, or from here I can put 0, or one more thing, let me write this side also. This is 6 volt, this is 6 volt over here, means voltage is given as 6 volt while current is 0. So when I write V is equal to E minus IR over here. Now see what is EMF. This says three identical cells in series. Three identical cells in series. So this we'll discuss it in the next class. When the cells are connected in series, the net resultant is given as 3 times the EMF. Their equivalent EMF is given as 3 times. This you can just remember it for now. How and why we'll discuss later. But right now focus on this question. So this is 3E. Okay. Here it is 3. Now if I say voltage is 0, this is 3E minus current is 1. This is equal to R. Okay. And from here this is equal to 6. Voltage is 6, right? Is equal to E. Okay, we'll have to calculate first. Now, see, along with every resistor, Safrina, let's say resistances are. So these resistors in series will also give equivalent resistance as 3R. Now, why is this? Again, this is a part of the next portion. But since it's a question from your board exam, and this is a very important question, so you should understand that chapter whenever a question is framed, it comes from any portion. Okay, so see, this is 3R. So we can say this will also be 3. So we can say 3E is equal to 3R over here, right? This can be written, right? Now, if I write 6 volt for voltage here, and E is, let's say, 3E from here, this whole term will be 0 because current is 0. So what is EMF? EMF is equal to 2 volt. EMF is equal to internal resistance, so resistance is also equal to 2. This is how we have calculated. Okay, got it. Now see, now coming to this point. If I is 0 and V has a value, means this part. I is 0 and V has a value. This part, this means that key is open. Current is 0 and voltage is equal to